Yes, so our speaker today is again Scott Larson. So he's going to give his second talk on small resolutions of closures of k-orbits in flat varieties.
Okay, so thanks for the opportunity again. It's not often people let me talk this much about k-orbits, but I'm happy to do it. I really enjoy this stuff. So, okay, so here's the setup for today. I'm going to first talk about characteristic cycles and motivate the goal to find small resolutions. And look a little bit at how small resolutions can propagate. So once you have a small resolution, you can get a lot of them in different ways. And so finally, rather than just go through the second half of my dissertation, I mean, I guess the first talk was like the first half, but I'm going to try to relate. I see a lot of people in the audience know a lot about Springer fibers and Schubert varieties. And so I guess my goal for the last part of the talk is to be somewhat convincing that fibers of these resolutions are important for reductive groups, and sort of the same as Springer fibers are important for file groups and things like that. So that's the goal. And I mean, I should say it is very much related to the second part of my dissertation, but maybe some more small examples and be convincing about how I think about some of these things, and that's kind of the goal. Okay. So remember from before, we have a connected reductive complex group, a fixed torus and a Borel, and K is the fixed points of an algebraic convolution of G. And so again, I like to assume K is connected when talking about this, because the statements are easier to say. And all the examples I consider K is connected. So we have the flag variety G mod B, and I'm going to let B be the k-orbits on G mod B, double cosets. So then this piece of B is a k-orbit in the flag variety, indexed by an element of B, and then X of B is the closure in the flag variety of the k-orbit. So also some notation, let K upper B be the stabilizer and K of a base point. So a basic fact from David Vogan in 1983 is that the set of irreducible Harish-Chandra modules with infinitesimal character rho corresponds to irreducible Kf invariant local systems on K orbits of the flag variety. So, how do you get from a pair, from a K orbit and the irreducible representation of the component group of the stabilizer? How do you get from that to a local system? So here's what you do. So the K orbit is like the group, not the stabilizer. And so what you do is take, maybe I'll let E sub L be the representation corresponding to L, the vector space. And so you can look at this quotient here. And so that projects onto the K orbit, and so that's how you get these local systems on K orbits. So it is describing it like a quotient like that, so that I guess maybe a basic principle for today is describing a lot of spaces isomorphically in terms of quotients like this. So that's a repeated theme. So what do we do with local systems? So we can extend the local system on the K orbit to the closure using intersection cohomology. So this is some complex of sheaves, well defined in the category. And so what we'll consider is the cohomology sheaves in different degrees. And so this is also present in David Vogan's paper. If you know how to calculate his Kazhdan-Lusztig-Vogan polynomials, then you can get a cohomology sheet. So this is something that, for example, Atlas of the group software can calculate. And so I've spent sort of a lot of time calculating these with Atlas of the groups. And so, for example, you can compute which k-orbit closures are rationally smooth. So what is rationally smooth? If you have the higher degree cohomology sheaves are 0, and then the 0 cohomology sheaf just looks like the constant sheaf. Then it's something like Q smooth or rationally smooth. So maybe just a comment, I'll say Q smooth instead of rationally smooth because there's examples of closures of k-orbits that are singular with rationally singularities, but rationally smooth. So I'm going to distinguish between rational singularities and Q smooth. Okay.
So the answer that you wanted that really
Sorry, this is a pair. So I'm thinking of the cohomology sheaf is something like
in the right hand side.
yeah. So I'm thinking of as like a pair EL. So this is just like the trivial local system on each orbit less than E. So it just looks like a constant sheaf on the closure of the orbit. Okay, so we're studying Harish-Chandra modules here. So a basic invariant of Harish-Chandra modules is the characteristic cycle. So this is, I guess, a good reference for this is Adams, Barbash, and Vogan's book on the Langland's classification of real reductive groups, so something like that. So they define the characteristic cycle and use it to study Arthur's conjectures and unipotent representations and unitary dual and a lot of this. But sort of the problem with it is there's not like a good statement. Not many people know many of these computations, and so what does it really mean in Harish-Chandra modules? It is a hard question. So what it is it's a cycle in the top degree Borel-Moore homology of the conormal variety in the cotangent bundle to the k action. So and over each of these conormal bundles of k orbits, we assign a multiplicity. So then the characteristic variety is just the support of this. So if the multiplicity is non-zero, then you include it. Okay, so that's the characteristic variety. So one thing you can say about this is that the image under the momentum map of the characteristic variety is the associated variety. So the associated variety is also something important for Harish-Chandra modules. David Vogan talks a lot about the associated variety here. Recently, there's applications to K-covariant K theory and the nilpotent of K orbits on the nilpotent cone, and so on. Okay, so it's like a refine. I think of it as like a refinement of the associated variety. Okay, so there are some things that are known about the characteristic cycle. I mean, originally, it was Kazhdan-Lusztig conjectured a lot of these things were irreducible in type A, and then Bressler, Finkelberg, and Luntz computed all characteristic cycles of Schubert varieties, and they described some condition on the Bow group element to say that all these things are irreducible.
Is this PCX study or you mean like this?
Yeah, that's a good question. So they were considering Schubert varieties. So I'm thinking like B, and I guess I'll talk more about this towards the end of the talk, but B equals W, I'm thinking about the Bow groups. So B cross B orbits. So I'm just thinking about the Bow group as B cross B orbits on B. But I mean, it's like a local thing. So it would also be the same for. It's like equivalent for thinking about diagonal orbits.
So you want to get that K
K would be G. Yeah. and that'll be an example that comes up later. So, yeah, good. Yeah, so Bill's asking if this XW is a Schubert variety or a K-orbit for the diagonal P action. And Ressler-Finkelberg and Lutz actually consider Schubert varieties, but I'm just saying it's also equivalent to the other case. And I guess I want to point out that their method here was using Zolovinsky's small resolutions. Zolovinsky's small resolutions that we talked about last week. Okay, so that leads to irreducible characteristic cycles. Let's see, Bo and Fu have a result from 1997 to compute in a different method all characteristic cycles in Hermitian symmetric spaces. So that was a generalization of this result using different methods and a generalized type C and D. Okay. And now more recently, Barcini and Zero have computed all characteristic cycles for any highest weight Harish-Chandra module. So all of these are like a Schubert variety case. And there's also some results for K orbits. Okay, so Barbash-Evans, with their small resolutions, actually said enough information in their article using general principles to say that the characteristic cycles are irreducible for UPQ and Gauss-Meier like varieties. And more recently, a student of Sam Evans has computed all of the characteristic cycles for K orbits and Gauss-Meier. So maybe I just want to mention here that I've been working recently with Timchenko on K orbits for isotropic Gauss-Meiers for the symplectic group. So hopefully we'll be able to say some things there eventually. Okay, so I want to just point out one trick for using small resolutions to compute characteristic varieties. So here is an image taken directly from Kashiwara-Shapiro's paper. So maybe just let me sketch what this all means. And maybe also let me say how I'm going to apply it to our resolutions here. So remember our resolutions, we have like some smooth map to a K-orbit closure. And if we include that in the flight variety, then we have, so let me say this is the resolution and this is inclusion. So if you let F be the composition, then you have a morphism of smooth manifolds. And so that's how you get here to a morphism of smooth manifolds. Okay, so let's see. So we need some complex on the smooth space. So I'm going to take G to be the constant sheaf. Okay, so that's going to be this notation on Y. So then the basic fact for small resolutions is that if you push forward along the constant sheaf along the small resolution, we saw this fact come up last week, then you get the intersection cohomology on the image here. Let me say of Y, and then you extend it to 0 and all of that. So this is on X, this in space. Okay, so oh yeah. Sorry, I looked up here. Switching notation. Yeah. Yeah, the image of Y. Yeah, thank you.
So at the very top there,
yeah, thank you. So this is like the smooth space. Well, X is still the flag variety, and then I guess Z is like the Caribou closure. Yeah. Okay. Thanks. Okay, so if we apply this to in this situation, we'll say the singular support of intersection homology on Z is contained in whatever this thing is, and I'll describe this. Singular support of G, and G is the constant G. Okay, so now let me explain what these what their notation is. So they start with y to x as the smooth map, and so as a tangent map. Okay, and then call this pi. Oh, and it factors, so this tangent map factors through the pullback. So let me actually draw the pullback here. So really I want to say that this composition is the tangent map. And they call this prime, and they call this like pi, like this. And then just by duality, they get the picture that they're actually wanting to look at on cotangent bundles. Okay, so we still pull back. I'm just still going to call this pi because it's still f. Look at the pullback here. And by duality, this arrow reverses. Okay, and so this is f prime transpose, and this is still the f pi. So that's the diagram that they look at. Okay, and so what's nice here is that the singular support of the constant sheaf is just the zero section. Maybe let me use a different color. So that's the zero section of the cotangent bundle. And so, so what you're doing is you're looking at, you're embedding y as the zero section and looking at the pre-image and then the image. And so it's saying the characteristic, if there's a small resolution, it gives some upper bound on the characteristic variety of intersection homology. So, so this is present in Kashiwara Shapira, but I actually learned it from let's see, Alexander Valenson. I get Valenson and Bernstein mixed up, but it was Valenson, and gave a YouTube video and said and gave this formula, and he said that this gets you pretty far in calculating singular supports of these sheaves here. Okay, so that's our main motivation for computing so many small resolutions. And so what this is saying is you want to find many proper maps to K-orbit closures to find bounds on the characteristic variety.
I'm sorry. So the single support of the constant sheaf is zero section. So then you're taking the zero section that up there, and then you map that to this fiber product. And you map that to the. So where? So you're.
Oh, I see. Yeah, that's the idea. I copied that down now. There's an inverse there.
Okay, so you're.
Yeah, so you put the inverse there. Okay. 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 So here's an example that I went through and I found interesting, so I wanted to share it. So so for B3 and C3, so now I'm picking file groups and Schubert varieties. Okay, so Schubert varieties. So it's possible to go through all of the Schubert varieties in C3 and find that there's exactly 36 Schubert varieties with small resolutions. And it's of the same form that I'm talking about, nothing, no tricks going on here. And so also, you can also conclude that the remaining 12 Schubert varieties do not admit any small resolution. So not just of the form mu, but like you can conclude there's no small resolution at all. Yeah. So I'm glad. So Bill asked, how can you conclude that there's no small resolution? And there's two tricks that come up. So here's an image from Montford's Red Book, his algebraic geometry book. And maybe just a comment here, I'm thinking about this as all k-orbit closures. So k-orbit closures intersect every single part of this image. And so you can find k-orbit closures in all of these places. So let me highlight in yellow the places you can find small resolutions. So if your variety is smooth, then any automorphism is a small resolution. And in fact, that's the only small resolutions of these. So you can find small resolutions there. If it's factorial and singular, then there's no small resolution. So that's one way of excluding some of these. And if it's normal, I'm just going to highlight like some of the normal ones have small resolutions and some of them don't. And if you know that it's singular, normal, and rationally smooth, then you can also conclude there's no small resolution. So those are the two methods that I use to conclude that some Schubert varieties do not have a small resolution. You can find rationally smooth locus different than singular locus. And you can find factorial Schubert varieties there using, I think it's called Monk's formula. So there's a paper of Alex Wu that gives a method for computing factorial Schubert varieties.
Basically, you're saying you're normal and you're singular. So if you're factorial and you're singular with no smaller.
That's right. Yeah.
If you're normal and you're singular.
If you're normal and singular and you're rationally singular locus, it's not your singular locus. Then it's not small resolution. And if it's not normal, I don't know. I don't really know what happens. So there can be some up here, but I can't really conclude that there's no small resolution. I haven't been able to do that. So okay, and maybe so you might be thinking, how many of these are smooth? So I think there was actually only 8 Schubert varieties that were singular with the small resolution. So this number is smaller if you exclude the smooth. Okay, and kind of interestingly, the small resolutions that were constructed also carried over to B3, but things are a little bit different. So you can actually find more small resolutions in B3. It was kind of surprising because I mean there's like the same Park-Sitter group, but the singularities are different.
But the rationally smooth are the same. They differ some of the
Yeah, that's right. Okay, and so what I was able to do with this work is I computed that all of the small resolutions have smooth and reduced fibers. Using just these general facts, you can conclude that the characteristic cycle is irreducible. So using the previous trick. And then also using previous work by, I think it's probably in Bowen Fu's work, but I mean, I was using my advisor's work because I was more familiar with that paper. So using previous work, you can find some characteristic cycles, some multiplicities in here, using the small resolutions, and then a trick of McGovern that propagates different multiplicities around for the Schubert varieties. Actually, I was able to compute all of the multiplicities of characteristic cycles for this file here. Okay, so I mean, I found that example interesting. So, I mean, a common theme in these characteristic cycles is they propagate. In fact, Harish-Chandra even used that word in their introduction to their book. Singular support like propagates. And so here's a couple of ways that you can find more small resolutions given just one small resolution. So given two algebraic varieties with a p equivariant small resolution, so here this is a parabolic subgroup in the complex reductive. So if y and z have an action of p and the small resolution is p equivariant, then you can construct a g equivariant small resolution just by looking at this quotient product like this. Okay, so how I apply this to k orbits is I think k equals g, and so the goal becomes to find explicit isomorphisms of k orbits with something. So here this is a parabolic subgroup in k, and then y is usually like a product of smaller k orbits or something like that. So if I can find a smaller resolution of the smaller k orbits, it propagates to this larger k orbit in a bigger group. So that's one way. And here's another way. So if you have a small resolution of a k orbit in a generalized Lie variety, like so in something like G mod P, then you can pull it back and get a small resolution in the full Lie variety in G mod P. So this is just the pullback, and you can describe it. Here's the quotient. So you stick on the end of a P mod B, and you get the pullback. So I don't know, maybe just a simple example here. So if we saw a lot of examples of small resolutions of k orbits were just like, let me use the same notation I have here. Just the restriction of projection of Lie varieties. So here, this is like m equals 0. Then if you pull it back to G mod B, then it looks like this. G mod plus bar, G mod B. So that's the pullback. So so any small resolution you construct in the smaller Lie varieties, you get for the full Lie variety. And I'm interested in that because this is like where the representation theory all takes place, is in the full Lie variety. Okay, and so I want to talk about k orbits in G mod B. And so a way to parameterize many of them is using something called a clan. And so I said briefly how I think about a clan. So there's always this map from KGB to W, and the image lies in the involutions. So in solutions. So one invariant of a k orbit on G mod B is an involution in the Weil group. So that's part of the clan, and then kind of like, I mean, so if you think of, if you think of the Weil group as the normalizer of the torus, mod the torus, you sort of have to keep track of the extra part from the torus to keep track of the plus or minuses. Okay, so this is a common way of parameterizing k orbits on G mod B. Okay. So here's my favorite group. So I was able to get Atlas. Atlas will pretty much output this automatically with a little bit of work. And write that. This is from Atlas. I mean, I was also able to check this diagram by hand. So what this is the Haas diagram of the closure relations of k orbits on the Lie variety. So let me spend some time just talking about the different things you can get from this image. So up at the top, this is the open orbit, and down at the bottom, these are all like Lie varieties for k, the closed orbits. These are all like isomorphic k mod for L and k. So these are all smooth on the bottom because they're closed. And there's one other really common way of getting smooth k-orbits, of k-orbit closures. So let me talk about that. So this is called a cohomologically induced orbits. So what is this? So if you consider the projection of Flake varieties to generalize Flake variety like this, sometimes you will project onto a closed orbit. So actually, let me start with the closed orbit down here. So Y is a closed orbit. Okay, and so the cohomologically induced orbits are preimages. Yeah. And so since Y is closed, it's smooth. And since this is the whole pre-image, you get some fiber product, some fiber bundle where the base is a smooth k-orbit and the fiber is just like a P mod B. So some smooth space. So this is a common way of getting smooth. So actually, so this will be like a P B, and this will be a smooth, right, B, a smooth k-orbit closure. So for example, in the group UPQ, which is a good group, it's a fact that all smooth k-orbit closures are of this form. So sometimes this really gets you really far in describing all the smooth k-orbit closures. So it's different here. So let me highlight all of the cohomologically induced ones. So any closed one is fine. In fact, any length 1 is also of this form. So these are all smooth. Actually, the open one is smooth also. Let's see. So maybe I'll just highlight a couple more of this form. So here's one. And so there's a few more, but let me just say that not all of the smooth k-orbits in this case are of that form. So so let me talk about this one here. So plus 1, 2, 1, 2 minus. Okay, so let that be B. Okay, so based on things I said in my dissertation, I mean, I was able to say that this looks like this has this form, K cross some parabolic, and then some smaller parabolic subgroup in the fiber. Sorry, some smaller k-orbit closure in the fiber. And this actually corresponds to the k-orbit in this smaller Flake variety 1, 2, 1, 2. Okay. And so let's see. So I want to talk about tau B. Remember, this is the set of all simple reflections such that this happens. So in this case, if this is U, then tau of U is just the second simple reflection. The second simple reflection. So that so this is in the group SP4R, where there's actually just 2 simple reflections. So this k-orbit closure actually comes from one of the k-orbits that we talked about last week from an isotropic Grassmannian. So if you look at this one, so k equals 1. There's there's always just four orbits if k equals 1, and the n is at least 2. So it looks something like, here's the orbits in the Flag variety. And so this, remember these are parameterized by A, B, and C with some conditions. This would be the open one, this would be the closed one, this would be another closed one. And then here's the mysterious one. And so using local coordinates, you can say that this one's actually smooth. Okay, so it's not a closed or open orbit, but it is still smooth. And so smooth closure, yep, smooth closure. And so you can actually say that you can use that to conclude that this one is smooth and it's not one of these cohomologically reduced ones. Okay, so various tricks like that come up here. I don't know, maybe if I have time at the end, I'll come back and talk about some more, but I want to move on here. Okay, so fibers, and let me just say fibers of the resolution here. So what happens if n equals 1? So there's just a single Schubert variety. And here I'm also simplifying to the case in G mod B, so I'm only looking at quotienting by B and n. Okay, so then in this case, you can say that the fiber is isomorphically an intersection of the k-orbit closure with the translate of the Schubert variety. So this intersection is taking place in a Flag variety. So you can describe the fiber isomorphically, which is great. But I mean, one of the things I was not able to do is to say what the dimension of this is. So I mean, in further work, I think this is one thing that should be done. What is the dimension of this? In small examples, it's possible to say, but I think it's possible to be able to get some description in terms of like what root types are involved in this W action on B kind of a thing. So that should be the type of description you can get, but it's hard.
That would tell you when this is small version.
Yeah, that's right. Yeah. So just briefly here's an example. 1, 2, 3, 1, 2, 3 and this is from the same SP6R. So if you take this as B and this is W, then I mean this is the type of description you'll get. So using this intersection, those are the fibers, you can say that. And so looking over the fibers of each, looking at base points of closed orbits, I think I'm going to write that because it's useful. Base points of closed orbits. You can go back. So 1, 2, 3, 1, 2, 3.
The first two lines.
Yeah, I think there's just a negative sign that's different.
Oh,
yeah, like the -3. It's very similar. Just the plus and minus has changed. So 1, 2, 3, 1, 2, 3. That's like that's way up here. And in fact, all of the closed k orbits are in the closure. And you can check using that description that it's a one-dimensional fiber over. Looking at the colors. Let me use pink. So it's a one-dimensional fiber over these two, and the rest of the closed orbits, it's a zero-dimensional fiber. And then just using upper semi-continuity of fiber dimensions, you get that all of the rest of the fiber dimensions are 0, and you can conclude it's a small resolution from that. So that's a common trick. Okay, so now I want to talk about this example here. If G is a complex connected reductive group, so now K is the complex group you start with, and then the big group is like G cross G. So you're looking at the diagonal copy of G and G cross G. And in that case, all of the k orbit closures, you can describe using this this fiber bundle, this quotient that gives you a fiber bundle. So the fiber, well, let me say the base will be the whole Flag variety, and then the fiber is the Schubert variety, and this W is the biogroup of G. So that's what all these k-orbit closures look like. And it's a way of having a lot of equivalence between k-orbits for the complex, if GR is complex, and also the equivalence with Schubert varieties. So you think of k-orbits as like a generalization of Schubert varieties.
And that equation XP is some things, right? XP is the closure of Q or a diagonal.
Yeah, that's right. So Bill says that XV is different than this XW, and that's right. Yeah. So V is always KGP. Yeah, and yeah, it's a little bit bad. So the notation gets a little bit bad. So in this example, G is G cross G, and K is G. G is something like G cross G. And so then if you're looking at the file group, it should be something like W cross W. But actually, I just mean here W is B. So,
Yeah, no, I just make that one here. That XV is really a K orbit in G, it's a G orbit in G cross G.
yeah.
The XW is sort of a single.
Yeah, and that's right. Exactly. The next W is the symbol. That's right. Yep. Okay, so I mean, based on this isomorphism, I just think of V equals W as like the generalization. Okay, so in this case, I can actually describe the dimension of all those intersections. So this was mentioned. Matthew Douglas commented to me that this intersection looks a lot like work of Curtis. So Curtis considered a refinement of the Bruhat decomposition of the Flag variety. And using his work, he can describe dimensions. I mean, first you have to reduce to the case R equals B. Then you have to find a finite stratification to reduce to Curtis's varieties. And then using things what he calls K sequences, you can describe this dimension. So it's some work, but I actually put this into a computer and it works pretty quickly. So it's kind of nice. Okay. So here's an example I used that from. So all Schubert varieties. So here I'm thinking of, I say AN minus 1 because that corresponds to W equals Sn. So if you go up to n at most 6, so up to S6, you can describe exactly what Schubert varieties have small resolutions. So the ones that do have one of the form that we've been looking at, and the ones that don't have factorial singular locus. But then if you go up to S7, here's the smallest one that I actually don't know. I don't know if this has a small resolution or not. And it was kind of interesting. I was talking with Alex Wu, and this is the same Schubert variety he has on his list of the smallest Schubert variety he can't compute. I think it's the Gorenstein locus of, using methods of Cortez, and I'm not exactly sure all what he's doing, but it was the same Schubert variety we came across. But okay, so using a resolution of this form, just like two Schubert varieties in the resolution, you can actually find a semi-small resolution with no exceptional divisors. So if you're just looking for the intersection cohomology, you can use the decomposition theorem with a semi-small resolution. And singular locus, you can compute using the no exceptional divisor. It's an interesting surprise for me there.
So the exceptional, when you say exceptional divisor, you mean like you're taking the dies or the singular locus? What do you mean by that?
Exceptional divisors. So that would be like a codimension one locus in the domain that is not an isomorphic locus. So it's collapsed. Okay, so continuing with Schubert varieties. So here I'm saying sigma of W is the support. And so this kind of goes along with the tau invariant. So we have two basic functions from the valid group, two subsets of simple reflections. And so one thing you can say about this, this map here is exactly when it's an isomorphism. So ignoring when this is smooth. So just any D and any W here, it's an isomorphism if and only if intersection of supports is contained in an intersection of tau invariant. So sort of a simple combinatorial relation on exactly when the map is an isomorphism. So here's, I mean, this really surprised me the first time I saw it. So for example, we have tau of W equals sigma of W, if and only if GW mod B is some parabolic subgroup. So if you apply that to the case of two parabolic subgroups here, I'm going to look at the support. Okay, let me just write the left-hand side. The support is I naught, and the support of this one is I1. And you get, and the right-hand side is the same thing. It's very surprising the first time I saw this. In other words, this is always an isomorphism. Okay, this is always an isomorphism, and then furthermore, you can do a little bit better. W is just whatever this image happens to be. So, yeah, so that's, I'm always writing. Yeah, the question was what is W, and it's just whatever the image is happens to be. So then you can do a little bit better. You can also say I naught is the left, I mean tau W inverse, that's the left descent of W. And then you can also say I1 is the right descent of W, tau of W. So this, let me just say, can assume that. And so this is a basic principle that comes up a lot. You always want to consider the largest group acting on the variety, or this is equivariant. And so taking I naught equal to this and I1 equal to this gives you the largest possible group that's acting equivariantly. Okay, and so so this leads to the basic question: when does the restriction of projection of light varieties, when can you restrict that to a Schubert variety and get a fiber bundle? So this is work of Ed Richmond and William Slofstra. Slofstra described exactly when this map is a fiber bundle using something called a BP decomposition. And I asked him like what the fiber bundles look like, and he said it would be an interesting result to describe what they look like. And so I was able to use this description of these maps to say that, well, actually, all of the fiber bundles you get look like this quotient here. I know I went a little quickly over that, but so it gets me to the point I want to say. They also describe, so this is this work is also being used in part 3. It's very non-trivial statements here. So what they were able to do is they say exactly when any Schubert variety is smooth based on if it's smooth, it's some iterated fiber bundle of smooth things in Grassmannians. And so using this description, I was able to say that any smooth Schubert variety, as long as the valid group generated by the support is simply laced, any smooth Schubert variety is actually a quotient, is like a product of parabolics with just the quotient there. And the thing that I need here, and which was really the hardest part about what I did, is that you can assume I naught is tau W inverse, and I1, sorry, I1 is actually tau W. So just one more slide. Yeah. Okay, so what I can do from work in my dissertation is describe all of the fiber dimensions if all of the Schubert varieties are parabolic subgroups. So let me just kind of skip over. I mean, here's the formula, but let me skip over that. But there is a formula for fiber dimension in this case. And so if the file group you're working with is simply laced, I mean, for example, in like UPQ or something, then what you can do is replace each of these GW1s isomorphically with this like product of parabolic subgroups. Quotient it out. So I mean, different parabolic subgroups here. Different M. So you can replace each little factor there, the G sub W's, with this product of parabolic subgroups. And this is where it's essential to make sure the quotient is still well defined. You have to make sure that you can replace it equivariantly. And so, I mean, using this, you can actually describe all of the fiber dimensions of any of these resolutions. So I mean, it's interesting, right? Like in general, I'm like stuck. I can't describe the fiber dimension here. But if it's simply laced, then actually all of these fiber dimensions can be computed. Okay, so let me stop there. Thanks.
That it's simply laced issue comes up too, because like because B and C are sort of expecting the values are the same, but you don't expect the answer to be the same. More the size of the value. Yeah.
Yeah, so I mean, for me, this is what Richmond and Oscar says. And so that's where this hypothesis comes. Actually, it's not true if it's not simply like there are examples of Schubert varieties that aren't blue Schubert varieties that are not in flat lines. You can make that. So these times do not smooth in general. That's right. A lot of the small resolutions that I've looked at for K-orbits do have smooth fibers, but yeah, they don't have to. That's a good question. I don't know the answer for sure, but I think no.
So when you take the moment of these fibers, do you expect some action of some other way, however, sometimes we have to do.
Yeah, I guess there's I mean, this is out of my comfort zone, but the action of the Harish-Chandra definitely comes up. This is out of my comfort zone, but people have told me to look at the Harish-Chandra. So yeah, if you like Harish-Chandra, it should be more. I mean, so I guess like if you look at semi-small resolutions and use the decomposition theorem, see if it fits. Are there any questions from anyone at home? Don't think so.
The speaker, yeah.
Bye, everyone.